Okay, we have a force of 125 newtons being applied to a wrench at a 15-degree angle to the handle. The handle is going to be our line of action because it goes from the pivot point of the bolt straight radiating outwards. And the force is being applied at 0.3 meters from the pivot point. We're looking for the torque according to this problem. Torque is force times radius times the sine of theta, again in degree mode. We have 125 times 0.3 times the sine of theta, sine of 15 degrees. We're just going to put that into our calculator. 0.3 times times 125 times sine of 15. We should get something near 9.7 9.71 Newton meters. A force of 2F is applied to a wrench at an angle of theta to the handle. The force is applied R meters from the pivot point. Derive an equation to calculate the torque applied to the wrench. Well, we're going to start with our normal formula, force times radius times sine of theta. All we have to do to this, it looks like, is just multiply the force times 2 because we have 2F. So torque is 2F times radius R times sine of theta. Pretty simple. Number 3. In question 2, if the force is quadrupled, so now the force is 8F, and the length is cut in half, 0.5 R, how does that affect the torque that results as compared to your answer in 2? So we're going to set this up much the same way. We're going to say torque is force times radius times sine of theta. In this case, it's 8F times 0.5 R times the sine of theta. We can kind of consolidate numbers because we're multiplying. So 8 times 0.5 would be 4F times R times sine of theta because it's essentially 4 times R times 4 times F times R times sine of theta. Once we have that and put it together, we can see that we went from 2F R sine theta to 4F R sine theta. So essentially the torque is twice as large. It is doubled. Number 4, we have a gear and it's telling us the torque is 857 Newton meters. The gear has a radius of 0.05 and they give us the angle of 30 degrees. The degree measurement that we are concerned with is that from a line of action to where the force is applied. The vertical line that they drew is not a line of action. It does not reach the pivot point. You can see that I've drawn a line from the pivot point, the center, radiating outwards, and then when it hits where the force is being applied, that is the line of action, and that angle between those two lines, that's the angle that we use. The vertical line does not hit the pivot point, so 30 degrees is not useful for us, except to say that we need the complement of 30 degrees to know that it is 60 degrees. Torque is force times radius times the sine of theta. So we would have a torque of 857 Newton meters. Theta is going to be 60 degrees, radius 0.05. We're solving for force. Torque is equal to Fr sine theta. 857 is equal to F times 0.05 times the sine of 60. Now you could also look at this and we could look at the other side of the angle and someone could argue that, well, what about the 120 degrees going from the 60 degrees or from the force to the other side of the line of action, and the sine of 60 and the sine of 120 are actually equal to each other. So you could use either side, doesn't matter. Once you do the calculations, you get 19,791.57 newtons for the force for number 4. Number 5, if the gear's moment of inertia, or also known as rotational inertia, or the I, is 130 kilogram meters square, what is the angular acceleration as a result of the torque applied? We know that torque is equal to I alpha, so alpha would be equal to torque over I. The torque they gave us in the previous problem is 857, and they're giving us the rotational inertia of 130. 857 divided by 130 gives us 6.59 radians per second square. If the force from 4 and 5 is applied to the gear for 5 seconds, what is the gear's final angular velocity? Well, here we have to understand that the gear wasn't moving first. It's kind of an assumption, but we need that assumption in order to answer this question. Omega naught, the initial angular velocity is 0 radians per second. The time they've given us is 5 seconds. We calculated the angular acceleration, alpha, as 6.59 radians per second square. We're looking for the final angular velocity. We can use our rotational kinematics equation, WOTAT. Final angular velocity is equal to an initial angular velocity plus angular acceleration times time. And we end up with, well, the initial is 0, so I'm just going to kind of circle out to show that that's 0 and it's going to 0. 6.59 times 5 equals 32.95 radians per second. Going to the back page, we've got two kids on a seesaw. Usually the seesaws are balancing problems. We're balancing torques. If we have balanced torques, we don't have any angular acceleration. The system's in equilibrium. It's a constant angular velocity. Could be 0, it could be non-zero. What does rotational equilibrium mean? Well, equilibrium in any system, think about linear. When we said that something was in equilibrium, the forces were balanced. But now we're talking about a twist or a turn or an angular velocity, angular acceleration, that sort of thing. But we're going to keep our mindset the same. Equilibrium means balanced. In this case, balanced torques. Well, if you have balanced torques, there is no net torque. If there's no net torque, there is no angular acceleration on the system. It's at a constant velocity. It may be standing still at a constant velocity of 0, but it may have some value. But whatever that value is, it's constant. I answer the question as an object is in rotational equilibrium if the net torque is 0. This means there is no angular acceleration. And of course, you could go on to say it has a constant angular velocity, but I doubt that the seesaw keeps in constant angular velocity. Derive an equation to calculate the mass of the child on the left based on both children's radiuses from the center of the mass of the child to the right. So based on both children's radiuses from the center and the mass of the child on the right. Okay, whatever. So balanced torques, torque 1 on the left is equal to torque 2 on the right. Torque is force times displacement times sine of theta, but in this case, theta is 90 degrees, sine of 90 is 1, so I'm dropping that off. In order to calculate force from the child, it would be the mass times the acceleration of gravity, mg, force of gravity. So m1g times r1 is equal to m2g times r2. G's cancel out. m1 is equal to m2 times r2 divided by r1. If the child on the right is twice as heavy as the child on the left, which child must be sitting farther from the pivot point? Well, if you're larger, you have a larger force of gravity. And if things need to be balanced, if you're a smaller child, you need to be further away. If you can't increase the force, increase the displacement. So I said the left would need to be 2 times further, i.e., for example, R1 would have to be 2 times R2. Okay, now we've got two fidget spinners. One of them has a force being applied perpendicularly to the line of action. The other one is not perpendicular to the line of action. We can see that one has force of F, the other is force of 3F. They have the same angular acceleration. We just need to determine what angle can you apply a force at where the force is 3 times larger, but the angular acceleration is the same. So I'm calling the one on the left torque 1, the one on the right torque 2. And then I'm also showing a difference because theta 1, where I've labeled it now theta 1, this is the angle it's asking for. But theta 2 is the one that we use in our calculations because it is between the line of action and the force applied. So on the left side, T1, force times radius times sine of 90, which is 1, is equal to 3 times the force times the radius times the sine of theta, in this case, theta 2. Forces cancel on both sides. The F's essentially cancel on both sides. So do the R's. They cancel on both sides. On the left, I am left with sine of 90 is 1, so I'm going to leave it as 1, is equal to what's left on the right, 3 times the sine of theta. Theta 2 being. Divide 3 to the other side, we would have 1/3 is equal to the sine of theta 2. And if we were to kind of undo the answer, do the reverse sign, so on your calculator hit second sine, it has an open parentheses, do 1 divided by 3, close parentheses. When we hit enter, we get an angle of 19.47 as theta 2. We're not looking for theta 2, we're looking for theta 1, and we know that theta 1 plus theta 2 is 90 degrees. So theta 1 plus our 19.47 is equal to theta 2, or is equal to 90, I'm sorry. So then theta 1 would be 70.53 degrees. That is the angle that the question is looking for.